Differential equations, we're in section 4.3, day 3. We're still working with linear homogeneous differential equations. Today, though, we're going to look at higher order equations. And here's a general suggestion. You can definitely use C-solve on the TI-89. That is a very smart thing to do, either C-solve or C-factor. A C-factor is another way where you don't even have to type in the equation. You'll just see duplicate factors. So just type in alpha C, lowercase c, then go and hit the factor button and you can type that out. And it really can help you as you can deal with that issue of duplicates. So look, again, if we are assuming that y equals e to the mx would be a solution, it probably isn't going to be too much of a stretch to guess that you'd come up with something like this. And you could take 4 derivatives and substitute that in and divide out your e to the mx, but here's what you get. It's not a quadratic, it's actually a quartic, a 4th degree equation right here. You could do C factor here and use x instead of m if you'd like. Of course, here it's really not necessary, is it? It's m squared plus 1 times n squared plus 1. And guys, if we just focused on one of them, well, you could see very quickly m squared would equal -1, and then m would be plus or minus the square root of -1, and that's plus or minus I. And of course, that means there's a 0 out in front and there's a 1. Why do I write it this way? If you're saying, hey, as I solve for m, I get this. Well, here's your alpha, here's your beta. Alpha equals 0, beta equals 1. So the bottom line is you have this real frustrating issue of saying, oh no, I've got this duplicate and with complex solutions. My goodness, how do I deal with this? How do I clean it up? Well, listen, here's what we know. If we wouldn't have seen a duplicate, you would have said, hey, I've got this right here. E to the alpha x, C1, a constant, times cosine of beta x, another constant, sine of beta x. But now comes this real frustrating issue. You'd say, I'm getting an identical solution, this duplicate. Well, remember, we're just going to put an x out in front, and my word, then what? Just be careful. You're going to have to write a different constant, C3, cosine of beta x. That's going to be quite possibly a different constant. C4, sine of beta x. And again, what did we see? We saw that alpha was 0, beta was 1. Well, alpha being 0 means that e to this 0 times x is going to completely disappear, isn't it? And then without too much work, well, it becomes a 1, I should say. And then what? You'd have c sub 1 cosine of 1x plus c2 sine of 1x. Out in front here, you've got your x. This e to the 0x just becomes a 1. Then we'd have a c3 cosine of 1x, just a cosine x. c4 sine of 1x, you could just write it as the sine of x. Wow, look at that. There it is. You've got your solution. So let's take a look at initial value problems. A lot of times you're going to find that when you're solving an initial value problem and you substitute in all your initial conditions, you might find frustratingly that you've got a whole wealth of equations here, maybe 3 equations, 3 unknowns quite possibly. And as you'd solve, you may certainly solve by hand. You can do this on the 89. Guys, you can also do this on the 84. And I think the 84, I'm going to be really honest with you, I do think solving with a matrix is easier here. Let's do that. Let's just get our calculator going. Matrix, we can hit second matrix. And I'm going to edit. I'm going to go over to edit here. This is actually easier to type in on an 84. And you can see it looks like I've got 3 rows, you know, 3 different equations, but I've got 1, 2, 3, 4 columns. So this is really a 3 by 4 matrix. And look what's happening. If I highlight it in yellow, I've got A plus B plus C equals 10. Just look at the numbers in front. It's like a 1A, 1B, 1C. Well, here's your 1, 1, 1. Here's your 10. Look at the second row, 2, 3, 1. Well, there it is, 2, 3, 1. Constant is 15. 3, 4, 3, 32. Well, all we have to do is just type those in. Hit 1, enter, 1, enter, 1, enter. Then hit a 10. Then go 2, 3, 1, 15. Finally, you get a 3, a 4, a 3, and a 32. And it doesn't take you too long to have that and to see it. Now, what you can do is go back to your home screen. We're going to use the RREF, reduced row echelon. So I'm going to go second matrix right here, go to math, and we're going to go down to RREF. Oopsie daisies, let's get that back up. And then we have to say matrix A. So I'm going to go second matrix and just hit that right there. Don't have to close your parentheses. You could see what you get, 1, 0, 0, 1, 0, 1, 0, 2, 0, 0, 1, 7. Well, that's what we've got here. Remember, this was your A row, B row, C row. Your A is going to be a 1. Your B is going to equal 2. And what you've just done is you've solved quickly, very nicely, and that very well is going to help you know what you are looking for in terms of finishing off a problem. Now, I'll be real honest with you, so very often you don't need to do a reduced row echelon in a 3 by 3 matrix. This last example, we're just going to showcase what we're talking about, but it's an initial value problem. So look, if we assume again y equals e to the mx for this linear homogeneous differential equation, we'll get m squared plus 2m minus a 3 equals 0, and then we factor. Well, I think we can all factor pretty quickly. We know we have to multiply to a negative 3, but add to a positive 2. 3 and negative 1 will do that. You'll get m equals negative 3, m equals 1. And what will we have for an equation? Well, we'll have e to the negative 3x and a constant c2, e to the x. You can think, okay, well, that's great. Normally we're done, we've been done, but now today we're dealing with initial values. We're saying y of 0 equals 0. Well, that means x equals 0, y equals 0. Let's go ahead and find out what happens. So I have 0 right here, c1, well, this is going to be e to the 0, which is just going to become a 1. So, my goodness, c1 plus c2 equals 0. That's one of the equations that you could have. And then we have a second initial condition. We could say, well, y prime. Well, what am I basing this off of? Of course, I'm basing it off of right here. Take your derivative, and you can take that rather quickly. And we can do that. We're going to do that right now. We'll have negative 3 c1 e to the negative 3x with the chain rule, and just a c2 e to the x. But now we're going to have y prime of 0 equals 4. That means when x equals 0, y prime equals 4. So let's go ahead and put all that up in there. e to the 0, of course, is just going to get you a 1. So, wow, look at this. Doesn't take you too long to see you've got a second equation. And by the way, you could even solve this thing with a reduced row echelon. This is kind of like this right here, where we'd say, hey, we've got some equations. We're looking for these constants. We're trying to find out what C1 and C2 are. This is a perfect example, guys, where maybe you just want to solve by hand. I'm going to take the second equation and multiply it by -1, including the 4, by the way. And you might think, why are you doing that? The answer is for elimination. Right now, you can cancel this. You get a 4C1 equals -4. C1 equals -1 when you divide. But look, if you had 0 is equal to C1 plus C2, well, now I know what C1 is. It's -1. That means C2 is +1. Well, one other thing. Look at the top here. I'm going to recopy that. Y was equal to C1 e to the -3x plus C2 e to the x. Let's see, we had that right there. Well, now I know what these constants are. C1 is -1. C2 is a +1. So what you'll probably see written in the back of the book, if you're checking this, is something like this, and e to the x might even be placed first, but this is your particular solution that satisfies the initial value problem.